Okay, everyone, welcome back to Monday, last lecture before exam 3. So next time we're going to have a review session, and I'll try to do that early and post it early. So I can't promise, I haven't done it yet, but I'll try to do it on Tuesday and give you that much more time. The same rules apply. Just be careful about one thing, which is that this last third of the class is, I know it's a hodgepodge of just stuff. There's a lot of little facts. Instead of building towards solving this Schrodinger equation, this double differential equation with all the different examples, it was all kind of the same pile, just higher and higher. For this part, it's just a bunch of stuff. So you don't have to climb such a high pile. However, the amount of short answer questions, which the test is mostly composed of, is very large, right? So you're going to have to try to work on remembering more of the details than you had to in the first two exams. So next week we'll then have 2 more lectures and then a review session. And I may cancel one of them just to give you more time, but don't hold me to that either. Let's see, I don't have much else to say other than let's just review what we talked about last time. And what's terribly important is if I give you this information and I start asking questions about like, well, what's the rate, what's the mechanism? The problem is that what you don't know is this just a statement of these are reactants and these are products, or does it state that A, molecularly transforms into state C, A to C? Does it just go? Okay, so the difference is it's just a statement of the reaction stoichiometry versus it's a statement of the reaction mechanism. Those may or may not be the same thing. So that's terribly important. Now obviously instead of A goes to B, A goes to C, because what we ended up with last time was talking about a consecutive reaction A, B, C. Now this is the mechanism, and one of the hints, of course, is that I put little K's above the arrows, and those are the rate constants. Remember that rate constants and rate orders are the two things that I would express in a publication that get across all the information about how the kinetics of a reaction go, and that's kind of like what we do in science. Okay, so this is our reaction mechanism, and now we can write rate laws and then we can integrate them. So the rate law, don't forget to do this on the test. I can very easily, I should be able to write anything up here. A plus B goes to C plus D goes to E plus F. I could, goes to 2G. I could be able to just prattle on and on and on, and you should be able to write down the rate laws. You can't necessarily integrate them, but you can write down the rate laws, and that is, okay, we'll start with the first reactant A. The change in concentration over time, remember, it's going to be minus the sinks for A, and that's usually that there has to be a term with A itself in it, right? A is going to turn itself into B at rate 1, so that's going to be minus because A gets rid of itself. Remember, it's the actor in its own reaction, so that's where there's a minus. K1 is because that's how fast it goes, and it will go faster if there's more of it present to go faster to begin with, for all the reasons we talked about in the previous lecture. Now, this is a first order unimolecular decay. This is the first example that we did when we started on kinetics, and this is the integrated rate expression. Okay, so here's the integrated rate, here's the rate law or rate expression. Here's the integrated rate law, sometimes called integrated rate expression. Two expressions for the same thing, right? Sorry about that, but that's how it is. Okay, now a better example is B. B, the change in B with time has a positive component. That's because A will form B, so that's positive. It does so with a rate constant K1. And again, there generally is a sink, and B is its own enemy, so the more B that's present, the faster it goes away. So there's a minus sign. It kills itself, so there's a concentration of B, and it does so with rate constant K2. Okay, and now recall that these are the time varying concentrations. Having solved A as a function of time, I just plug that into here, and then you integrate it, and there's software that would help you do that. This would not be the easiest thing to integrate. So right, remember, you would bring the change in time over here. You'd integrate the left to get B of t, you integrate the right, and this is what you get on the right side. So the calculus, it was easy to do this one, isn't it? It can get much more complicated. And again, you need software or some 17th century math textbook. So this is B of t. Okay, next bit, C. C is a little bit easier because it's the final product, so there's no sync. There's only something that it forms from, so that's a plus component. B is the actor that creates C, so I have a plus concentration of B, and it does so with constant rate 2, rate constant K2. Okay, then there was a trick on this one, and that was to note that the stoichiometry of the thing is such that you have your initial concentration minus however much other things you have has to be the leftover, which is C, right? If this is your starting point, this is everything else that could be there. That's not C, therefore the difference is the concentration of C itself. Now we solved A of t, it's right here. We've solved B of t, it's right here. Again, it's a trick. We avoid having to do any integration, and the result is right here. And I hope you can write that down. It's a pain. You know, you don't need to memorize this. That's ridiculous. Anyway, you just get a flavor for it. You're just getting an idea how this works. Here is, for B, it's a bit more typical that you've got dB dt equal to some expression, and then you have to, it's a single first order differential equation that you just bring the dt over to the other side and integrate it. That's typical. Sometimes you run into tricks like we have for C, where there's some trick of stoichiometry, meaning that you don't actually have to integrate anything, you just have a bunch of algebra. There's always either you do it the hard way and there's a trick. It's always one or the other. So, okay, so that's really all I had to say about this, and I'm still just reviewing. But as we can actually get into more biochem, okay everyone, sorry, there was several people just walked into the room. That was strange. I don't even know where I was at. Let's see, I think I was talking about biochem. So as we move on into this lecture and the next lecture, I can talk a lot more biochem, especially like enzymes, enzyme kinetics. That's like a big thing. Enzymes are very important because they regulate like cell growth and, you know, tell cells when to grow, when not to grow, when to die. And if that gets out of control, then you've got cancer. That is literally the definition of cancer. So when I go to biochem talks, often, you know, enzymes are very important, and they talk about this one concept, and I've written it in when all the people came through. They use something called the steady state approximation, and they use that to analyze enzyme kinetics. So I'm going to show you what that is. Again, you bloody likely might see this in any kind of professional discussion on something like cancer, and since all of you want to be doctors, you know, this might be something that's relevant to you. However, let me point out something that it just kind of bothers me, and I've told you this many times. This class, if you could go back 50 years, this class is identical, right? After quantum and Maxwell-Boltzmann, the class is identical. You know, after they discovered that in the 30s, nothing's changed. But we have all these computers now, and almost no one ever uses them. Now, you see why I put a lot of questions on the problem set where you have to go to the Mathematica website, because we have computers and we should use them. And what I do is I ask you harder questions. Now, one of the things I haven't written your last homework set yet, but one of the things I'm tempted to do is have you use some online software that solves things like this. Basically, we have software that you can input some, unbelievably complicated. A goes to B, goes to C, goes to D, goes to E. You could have thousands of things turning into thousands of other things and back and forth. And the computer, it won't solve it like with either the K's and T's. It'll just give you like rise and decay curves, concentrations versus time, which it uses a numerical algorithm. So it's never using E to the T. It's just using a big table of numbers. Whatever. My point being is that anything you can come up with, a computer can solve. So we don't really need approximations. However, remember what I just said, when I go to professional talks, I often see this steady state approximation, so I need to talk about it. Okay, the idea of the steady state approximation is, so many things work this way. Something binds to an enzyme, and then the enzyme activates a cell, something like that. The idea is that the intermediate, whenever it forms, it also decays. So it never builds up concentration. That's the idea. It forms, well, there's more of it, but if it forms, it'll decay away, so now there's less of it, but you broke even. Now, the mathematical statement of that is that the concentration over time just is zero. Now really, it's this right here, but we approximate that as being zero. Okay, so what do you get for that? Okay, now since this is still equal to K1A minus K2B, now what you can do is you can solve B, and don't forget this. I know maybe it would help if I was a bit more careful on my notation, but when I write out these rate expressions, these rate laws, this is A as a function of time, and that's B as a function of time, right? So therefore, B as a function of time is equal to K1A as a function of time. Again, I've been actually leaving these out, so sorry about that. And so it's actually K2B, sorry, I forgot the bracket. Okay, and of course what we're trying to solve is the concentration of B. So there you go, right? And we know what A as a function of time is. You don't need any stupid math tricks to solve that. A first order decay is stupid simple, right? And that's the initial concentration. Remember how I told you I like to express kinetics as the concentration of reagents? It's because you control those. I always know what the initial concentration of A is because I probably scooped that into a beaker. So I know exactly what it is. And then everything else depends on that. So there you go. Okay, now C, let's do change of C. Okay, so what do I do here? Okay, the change in concentration of C with respect to time, and that's just right here, equal to K2B. And again, that's actually B with respect to time. So look at that, that's actually equal to K1 concentration of A at time 0. So notice that the K2 here, K1 over K2 times K2 is K1. There you go. Okay. Now to solve for the concentration of C over time, let me do this. I'm going to bring the change in C over here. Okay, so I just established this. So again, if it wasn't clear what I was saying before about how you bring the dt over, remember this is just how you solve a first order differential equation, which is like way, way easy and way straightforward because they're just simple integrals. Simple integrals. Remember to line up the limits. So if the lower limit is 0 times 0, what is the initial concentration of C at time 0? Will be 0. It's a product. Hasn't had time to form yet. Now remember also, and I hate to bring this up, but we often, if I'm integrating with respect to time, I often use the same time as the upper limit. That's technically a mathematical flub. I shouldn't be doing that. It's very common to do it. Now remember, I actually should be using like a big letter T. Or sometimes, again, if done correctly, you put a little dash by these T's, something to differentiate it. But the thing is, it doesn't really matter. The reason that most people do it the way I'm doing it, even though it's technically wrong, I don't want you getting confused that there's like more than one time, right? Because that's weird. There's only one time. Anyway, so what do we get? Oh, and of course, the concentration of C at time t is the concentration of C at times t, right? So this left side is the concentration of C at time t minus 0, because the initial concentration is 0. So there's nothing to do there. And then I've got this integral. I've got this integral here. And let's see here. It turns out that this is equal to a at time equals 0, 1 minus e to the minus k1t. Okay, now again, the way I go from here to here is I can look it up. Now I think I'm actually going to show you, I'll actually show you how to do this, but in a different example. This is actually kind of a lot easier than you think. But let's just say that you looked it up on a cheat sheet. You looked it up in a 17th century math textbook, right? Again, between setting it up, with all our software and our internet, if you can set it up, you're done. You should be confident enough to use Google to find things, right? Including things like this, or find the software that figures it out for you, which is, I told you, like when I have something like really hard to solve, which occasionally I do in my professional work, I actually use the professional form of Mathematica, which the school gives us. Okay, so there's this. All right, now the point of this is, cool, that's easier. This is the steady state answer for the formation of product. But what you get out of it is there's actually a little bit more, this is like way easier to interpret than this. But now there's something more you can get out of it. Under what conditions is this the real answer, right? Remember, this is the real answer. We're talking about the same ABC. When is this equal to this? When are those the same? What would cause those two to be equal? So let's go back here. So why would this equal a at time equals 0? Now that's a no-brainer. A at time equals 0, a at time equals 0. And then I've got 1. I've got a 1 there, I've got a 1. Okay, now I've got a divergence. I've got a minus, and I've got a minus e to the minus k1t. Okay, so how would this term turn into just minus e to the minus k1t? What would cause this to turn into that? Okay, now I can see here, I've got, minus k2t. That has to die off, right? So that means k1, I want k1 to be basically 0. So, therefore, k1 would basically be 0, and k2 would not be 0. Okay, there's a better, more logical way to say that. k1 is way less than k2. So not that k1 is necessarily 0. It can't be 0 because you never formed any b to begin with, right? You got to form a little bit of b. It's that k1 is much less than k2. Now let's look at that. So this term's gone, and I've got k2 e to the blah minus k2 e to the blah divided by what? K2. And that's minus e to the blah, blah, blah. All right, so there you go. Now what that means is that the steady state approximation is valid when k2 is really high. Now that means as soon as b forms, it's immediately gone. Right, so in other words, let me say it a different way one more time. K1 is very low, right? That means that you're waiting a long time for A to turn into B. You have to wait a very long time. It's, every second an A turns into a B. That's very slow, by the way, for chemical kinetics. 1 second, rate, that's really slow. Okay, so every second you get a B. And then 1 microsecond, 10 to the minus 6, it turns into C. That means you basically never have any B present. So those are the conditions under which the steady state approximation is valid. Now again, you got to think in terms of, why are we even talking about this? It's because back in the day, when these get more complicated and they didn't have computers, you were going to have to make approximations. And now we don't need to do that, but now there's a second benefit. It's when it makes the result easier to understand, and it may offer mechanistic insights if that approximation turns out to be valid. So those are the values, and that's why, again, you hear it all the time. Okay, let's do three more. We're going to do 3 more examples. And just example after example after example. Next lecture will be enzyme kinetics specifically. Okay. Now, of all the things you can think of, what else might happen? Well, A goes to B. Okay, now that's stupid simple. We've already done that. But A can also form C. So this would be like a competitive binding of a substrate. So there's some ATP, right? And ATP, several things use ATP. So you don't know what the use of ATP will be. Will it form B or C? So this is a thing, right? So let's solve this one. Why not? Okay. And again, it's good practice. Let's see. Let's change in A. Now this is probably what I will put on the exam. Is I'll write something like this and have you write the rate expression or rate law. Same thing. Okay. Now A has a sink, which is K1. A is its own sink here. If A is present, it will make itself go away by turning itself into B. That's why there's a minus. It's proportional to itself. And the rate constant is K1. Okay. Now, there's a second sink by K2. Okay, so there you go. Now, it turns out that this ends up being like stupid simple to solve. So integrate the rate expression, and you should be able to do this because it's still a first order deal. It's going to be the initial concentration, E to the minus, instead of K1T, it's K1 plus K2T. Right, so it's still an exponential decay, it's just faster. And why? Because A has 2 channels. So it like doubles the rate at which it can go to something else. So, and the way to solve this, of course, is that you would just factor. You just would factor the concentration of A out, and then do the thing that we did on the first day of class. I showed you how to solve this. Bring the dt over to the side and integrate. Again, it's very, very simple. And we've done it. Okay. Now let's do change in B. Now this is going to get a little more complicated. Here's the thing. You would think that this would just be stupid simple, right? This is an exponential decay. Well, the B would just be an exponential rise. I mean, maybe I don't even have to write anything down. It's just obvious. So here's one of the things about kinetics. Again, A goes to B is as simple as it gets. And this would be about the next layer of complication I could ever think to add to that. And guess what? It's actually going to it's really going to be a bit of a problem. And here, let me show you what I mean. Okay, so B is formed by A, so the change in B is positive. It's positive because the actor A creates B, so that's positive to create, and it does so with rate constant K1. Okay, now recall that, again, my pad shorthand, this is actually A as a function of time, and I've already solved that. Okay, so what's that? This is K1, A at t equals 0. I'm just writing what I already wrote down. K1 plus K2, T. Okay. Now let me bring the dt over. And of course what I'm going to do is I'm going to bring the dt over to the right side. Okay, now I'm integrating this, and I'm going to integrate this, and I'm going to integrate this from 0 to t, and this will be integrated from, the left side will be from concentration of 0, because initially it's a product, so at time 0 there's no product. So initially the product is 0. At time t later, there's a concentration B of time t. That's kind of like cheating, isn't it? Right? So it's kind of silly even that you even do this. Okay, now I promised you that, again, you're looking at this and saying, oh my God. Really, it's just integral of an exponential, right? That's a bunch of constants. I know that it makes it look like, oh, I don't even know what that is. Hold on one second. Hold on one second. Look at this. Integral of e to the ax. What's that? Sorry, those are x's that look terrible. Okay, what is that? That is e to the ax over x, right? Sorry, my x's are weird. Okay, so that's the integral of e to the ax. Now what have I got here? Integral e to some constants, which I call a, and instead of an x I have a t. But what does that matter? It's just a letter. Okay, so this ends up actually being quite easy. Let's see here. So, of course, exponentials always survive. Exponentials always survive. Okay, so I'm going to write down the constants. Remember, the constants of integration just come out. They always survive integration. The integral always, the EXPs, whether you're doing a derivative or an integral, they never go away. Okay, now, based on the identity that I very stupidly erased, you just divide by the constant, the minus a. And the minus sign I'll just put out right there. And did I do that right? Yeah, I did that right. Okay. So I integrated it. No, I didn't. There's a trick. That was an indefinite integral. That was an indefinite integral. We have to do a definite integral, right? Okay, so that means we have to apply the limits. And again, you see how it's kind of silly that I use an upper limit with the same letter of the integrand. That's technically incorrect, but regardless, it's not that hard to follow what's happening, right? Okay, so what this ends up being is, here, let me just do all the algebra. It actually ends up being kind of complicated. So I'm just going to write down the answer. And just assume that, you know, if I wrote down, I can apply the limits and then I get a term, and then the next thing I do some algebra and I get this. I'm just going to assume that you can do all the algebra. For some reason I'm writing crooked today. I don't know why, but okay. Oh, I don't like that. The zeros touching the bracket, that bothers me. There we go. Okay, so like I told you, you would think that this part, this b of t, would have been actually really quite easy. So, of course, this is b is a function of t. You would have thought that this would have been, I mean, I thought it would have been very easy, and it ends up being, you know, decently complicated. Now, you can do it, right? You just did it. But, you know, it wasn't nearly as straightforward as I would have thought. Okay, now let's look at c of t. So likewise, if you did c of t, you would have gotten this. And you'll see why I'm, you know, why am I even bothering with this? You'll see in a second. It looks almost identical. In fact, you may even have a hard time seeing where it's different. I'll show you in a second, so you'll understand why, you know, it's arbitrary what I call B and C, right? Again, my handwriting is bad today, and I don't know why, it just is. Okay, it's a little bit better, isn't it? Okay, so there's C of t. Now, you may have a hard time even spotting the difference, but it's actually right here, K2 and K1. So the rate, the concentration A or B B or C, the products over time, the expressions are almost identical. And why wouldn't they be? Because, I mean, it's A goes to B, A goes to C. The difference is K2A or K1 of A. Okay, now the point of that is, imagine that what you're interested in the ratio. What's the concentration of B, again, B over time, over the concentration of C over time? It ends up being K1 over K2. And so this is something that you've probably heard of before. It's called a branching ratio. Okay, so again, remember my original example. Let's say A is like ATP, the energy molecule, and it can go on to do one thing or the other thing. Which one it chooses to do is the branching ratio. And despite, it's unfortunate that the mathematics was a little on the harder side, it was. But the end result ends up just being a ratio of the rates. Now you could probably have just guessed that, but you don't really know. You don't really know. You can get surprises, right? Again, if someone showed me this and asked what the branching ratio is between B and C, I just would have assumed it's just proportional to the rates. But, and it is. And I had to do all this bloody mathematics to make sure. But I'm telling you, you got to be careful about making presumptions, because all this stuff, I mean, look how complicated it was. While the result was intuitive, it didn't have to be. So just, look out for that. Okay, one more example. Got 20 minutes left, so actually I got two more examples, and this will go kind of quick. Let me wipe out the board, and 2 more examples, and we're done. Okay, now, of all the types of things that could happen, we've talked about A plus B goes to C, 2 things reacting. A goes to B goes to C. I bet that's common. 2 things happening, 2 outcomes. A goes to B, A goes to C. Those are all very sensible. What else could I think of that would be like something that I would imagine happens a lot? That would be this: reversible reactions. Equilibrium, right? Now this is a big one, right? You can imagine. We definitely got to do this one. After we've done this one, I've actually covered most of the important examples. And then the next lecture will spend entirely about enzymes. Okay, so of course K1 will be the forward and K2 will be the backward. Now there's, just in case in your professional life you see this, people often call the reverse reaction K minus 1, and sometimes they just call it K2. So, sorry about that. I actually read a lot of literature that looks at stuff like this, and half the time they do K2, the other half they call it just K minus 1. It's not hard to follow along which one they've picked, and hopefully they stick with it. So anyway, okay, now, again, the thing that you should be paying attention to, the usefulness of this lecture is I'll probably throw something at you and say, write the rate expression. And you're going to be doing this. The change in, we'll start with the reagent. We'll always want to start with the reagent. And what is a sink? Well, A is its own sink as a reagent. So I better have a minus sign because it's going away. That rate constant 1, and it is responsible for its own demise. So there you go. So that's a sink, but there's also a source. Sources are positive. So positive what? Positive K2, and the source of A is B itself, its own product. So there you go. Okay. Now, I mentioned at the beginning of the lecture that there's always, sometimes there's a trick. It sounds like we need to bring the dt over and integrate, but there's a trick, and that is to do this. Right? There's no tricks with A, but for B, there's a trick. What you can do is say that B, by stoichiometry, will be the initial concentration minus whatever is not B. The leftover is B, right? So again, this is what you started out with. If you start out with 1 mole and you have half a mole of A later, that means the other half a mole has to be B. 1 minus a half is a half, right? It just makes sense. You don't derive this, it's obvious, right? Okay, now, I'll tell you what. I may have you do this on a problem set. I haven't written it yet, so don't hold me to this. But now I've got a deal. Now I've got a little math problem, right? And again, like the last example, it's hard to recognize that, oh, actually that's one I can do quite readily. It's just an integral of an exponential. Sometimes, like this one's actually kind of difficult. I was able to do this one, guess what? Wolfram Mathematica Online has one of the, it's like a whole bunch of different web pages for integrals and derivatives and matrices. You did a matrice, you did a zeros calculator. Guess what? There's a DiffyQ web page. Now, what you plug into that is like this. And I think you can figure out what's what. So I call that the change in A with respect to time y. Now let's see. I've got minus a constant, and the website likes A's and B's. And this is y itself. If this is the change in y with respect to time, then that's y itself. A with respect to time, that's A itself. Okay, so y is A. And I'm doing that, I'm calling it y because that's what the website wants. I actually, when I give you homework assignments, I've actually made, obviously I've made certain that it'll work and how to make it work in case it likes to hang up. So in this case, I made sure that I used the right letters because sometimes it's sensitive to that. Okay, then what have I got? Then I've got some constants, K2 times initial A, those are just constants, so I call that B. And then I've got minus C, which is K2, and again, this is Y. I know I've been really terrible about this. I'm really regretting that now, that if I just write A, it's really A as a function of time, so I've kind of been messing that up quite a bit, so sorry about that. Okay, now, then I hit go on the website and said, hey, what is y, which is of course a of time. A is a function of time. And the website spits out this, b over a plus c. Of course, b is k2, a at time equals 0. A is k1. Anyway, so yeah, I've got all this worked out. And then get this. I swear to God it does this. It has a question mark. E to the minus k1 plus k2 t. Question mark. What the heck is that? Okay, what's happening here is one of the bigger things about DiffyQ, differential equations, is remember how I keep bringing dt over and I integrate? And I have limits of integration. When you do DiffyQ type solutions, you need to have boundary conditions. Those are the limits of integration when you integrate. The translation to limits of integration for DiffyQ are boundary conditions. Let me say that again. When you integrate and you have upper and lower limits, you know what those are. Those are just upper and lower limits. When you are applying the same concept to differential equations, you don't call them upper and lower limits, you call them boundary conditions. So the question here is that Wolfram website, the DiffyQ solver, does not know the boundary conditions because I didn't tell it. So we need to figure out what that is. And here's how we do it. Okay, the first thing is I'm going to now insert A as a function of time. That's what Y is. Y is equal to B is, of course, K2 A at time 0, and over A plus C, that's K1 plus K2. Okay, plus, again, question mark, E to the minus 1 plus K2. Okay. So now our job is to figure out the question mark. Okay, now, the way to do that, at t equals 0, A of t better be equal to the initial concentration. right? I mean, duh. Does it? Does this expression do that? Okay, let's see. If I have 0 here, then this is actually not 0, it's 1. That means this plus that question mark has got to equal that. So you see how I did that? Again, e to the 0 is 1. So all of this is equal to, let me write it down. It's not hard, right? Okay, and then you just solve for that. That's how diffie-qs work. You have boundary conditions, and the solver doesn't necessarily know it. It's just one of those things you have to live with. Again, I'm always telling you, we should use computers to solve these things. But it isn't always that straightforward, is it? Okay. Now, what that means is that once you solve for that and plug it in, this is what you get. Maybe I should speed up time. But regardless, let me bring up another thing. Look how complicated this one is. This is kind of hideous. My God. Look at all that. I'm not even done yet. K1. Okay. So there you go. Oh my God. That's nuts. Okay. So, even something is, remember, we started with A goes to B. Unbelievably easy, right? We did that on the first day of kinetics. And then, all I do is I say, oh, well, it can go backward. And all of a sudden, it's a freaking nightmare. And I even need a computer to solve it, and even the computer can't really give me the answer. I tell you, I mean, it's really funny how these things really just mushroom out of control really, really quick. I'm really glad we got computers to do that for us. Okay, next bit. Let me point out one neat thing. Oh, I forgot a bracket there. That bothers me. Tell you what. Let's plug in t equals infinity. Let's see what happens. A at t equals infinity. What I'm trying to do is I'm trying to figure out the equilibrium constant, by the way. That's why I'm trying to do this. Okay, that would equal K2, A concentration of t equals 0, and that's because that would be 0 over K1 plus K2. Okay. Now, I didn't solve for B, but it would be the same rigmarole. Yeah, it'd be very, very similar. Actually, you know what that would be? That would be A at time equals 0 minus the concentration of A at time infinity. Right, again, so here's another little math trick. Instead of going through all of this over again to solve for B, I can just solve for it this way at time infinity. And then what you can do is it ends up being equal to what? K1 A at t equals 0 over K1 plus K2. Now, here's the neat thing. What is an equilibrium constant, right? So I'm writing an equilibrium, well, it's up there now. I'm writing an equilibrium reaction, and you were taught to express that in the form of an equilibrium constant. So let's do that. You should know that, right? Because clearly, the equilibrium constant, which we call big K, little k's are for rates, big K's are for equilibrium constants. That would be concentration of B as a product. Once, we'll say infinite time has passed, and divided by the reagent after infinite time has passed. And if you just look up there, it's not hard to see that everything cancels. It's just K1 over K2. So there you go. Okay, so there you go. There's really the last type of interesting thing that might be relevant to, like, especially bio, is equilibrium. That's obviously important. Last bit, because I don't have much else to say, let me tell you about something called, it's also relevant to Beacon Lab. It's called the Stern-Volmer. Stern-Volmer. Okay, what Stern-Volmer is how you do biological assays for activity of things, for concentration of oxygen. Terribly important, right? There is a huge number of biological analyses that are done with what's called the Stern-Volmer analyses. It uses a chromophore, an emissive fluorophore, and we do a lot of biological exploration with dyes. You know, I talk a lot about dyes, and I showed you that little quantum dot video, because dyes are really important. Now, it turns out that if a dye is in the excited state, and I'll call it A, so that's like our reactant, it can radiate, it can radiatively relax to the ground state by making light. Now, it can also relax non-radiatively, NR, to the ground state, and it does so by making heat. Okay. Now, we've just covered this. The rate at which the thing emits light, so what you can do is you can resolve the emission of light over time with specialized equipment, which is not particularly difficult. It looks like this. Okay. And K observed is, of course, K1 plus K2, K radiative plus K non-radiative in this case. Now, we often like to express this in a lifetime, tau, and tau will just simply be 1 over the radiative plus non-radiative lifetimes. Remember, we talked about tau before. It's just sometimes people don't like to express things with a rate constant per second. They like to express things in time, in terms of time itself. And so that's what a tau is. Okay, now, the way you do biological explorations with a Stern-Volmer is that you're looking for a quencher. That's your biological of interest. And a lot of stuff quenches fluorophores, like oxygen. Oxygen's a good quencher. Quenches just tons of stuff. Okay, so let's put the chromophore in the excited state, and we're hoping it's going to emit light. Along comes a quencher, and guess what? No light. Just A plus Q. I guess there's some heat. There's some association. That's like an association rate for those two coming together. Now, in this case, if you add this, K observed, this would be observed tau. We call that tau of Q. That's going to be the radiative plus non-radiative plus the association constant, and you need to, of course, have Q present. So all I've done is, this is really simple. I have simply added another channel for it to decay. So normally an excited chromophore radiatively emits, but it may just get hot, so that's why I added that. But now I'm adding another term because it can be quenched by our biological of interest. And Ka times the concentration of quencher makes sense because the concentration of quencher is 0, then you go back to the original form, right? So that makes perfect sense. Okay, now what that means is, what you do is you have 2 cuvettes. One is your dye, and one is your dye plus quencher. And what you could do is take a ratio of the 2. Now, it turns out that it's mostly true that this will be equal to the intensity of the chromophore. We'll call that I0. And divided by just the intensity, which would be the intensity in the presence of a quencher. Okay, it turns out that this ends up being 1 plus this associative rate with the quencher itself, and divided by everything else. And the way that this can be simplified is as follows. Okay. Association, tau, concentration of quencher. Okay. So, so what you can do is, often this is expressed this way. It's expressed as 1 plus something called a Stern-Volmer constant, kind of concentration of Q. Okay. So what you would do is you would have, let's make a graph, and let's say that we're looking for oxygen. Oxygen in a biological process. Let's say it's being consumed, and maybe that's good, right? So that would be like a normal biological process. What you would have is the dye without the quencher. You would do the experiment and measure the intensity, and you divide the two, which I know is like kind of weird. And let's subtract 1. And you do that as a function of quencher concentration. So as you add more and more quencher, you would see a line go up where the slope is proportional to the Stern-Volmer quenching constant. Okay. Now the important thing about this is that this is a really, really good way to probe biological activity. And the thing there is, and I can't really explain this further because I'd have to start bringing up specific examples, and I'm kind of out of time. But the important thing is that the Stern-Volmer constant itself is readily interpretable depending on your biological application. There would be a normal range, there would be an abnormal range, and whatnot. So again, biological assays, when done with fluorescence, which they're almost always done with fluorescence, uses a Stern-Volmer approach to analyze the results, with the slope being the Stern-Volmer constant, and that constant telling you about the normality or abnormality of the process you're watching. So, okay, with that, again, we're finally getting some real biochem. Next time, maybe the last lecture of the class, we're going to do a lot more biochem, enzyme, this and that, so I hope you like that, and I will see you then.